As the saying goes, if you don't learn from the past, you're doomed to repeat it, or words to that effect, which is why understanding what's happened to the Earth's climate in the past is critical if we're to make accurate predictions about the effects of climate change in future. So how might clams help? Well, they're among the oldest living creatures on Earth. Some of them survived for 500 years. And Georgia Mills spoke to lead researcher David Reynolds to find out how he's using them.
We've basically taken advantage of the fact that marine clams can live for an extraordinarily long period of time, for up to 500 years. And as they grow, they basically lay down growth rings every year in the same way that trees do. You can essentially regard them as the trees of the sea. And basically, as they're growing and laying down these growth lines, they are capturing the natural variability of the climate as they grow. So that's both in terms of the ring widths of the shells, but also in terms of the chemistry that's incorporated into these shells. We can go back with absolute dating precision and look at how the climate changed and really explore the timing of these changes with absolute dating precision. And it's that dating precision that's essential for trying to understand how the marine variability is important in the global climate system, because we need to be able to look at the timing of these changes in the ocean and relate it to changes in, say, the atmosphere or in the ice core records, and see how that all fits together much more closely.
And you mentioned the chemistry of the shell and the width changes, but how much can this really tell you about the environment?
Quite a lot. It's surprising actually how much information that we can get from these shells. So in this particular study, we were exploring the oxygen isotope composition of the shell material, and that basically tells us about the combined seawater temperature and salinity at our location. Now, if you choose your locations carefully, like we've done by looking in the north coast of Iceland, that variability in temperature and salinity will tell you a lot about broader scale circulation patterns in the entire North Atlantic, because it's basically situated at a frontal area where, depending on what's going on in the climate system and in the oceans, you'll have a different amount of Atlantic water coming onto the North Icelandic shelf or a different amount of Arctic water coming onto the shelf. And as that changes through time, it's being captured by these oxygen isotopes. And so just by looking at these shells and the chemistry of these shells, we can start to build a much bigger picture of how circulation changes in the North Atlantic have varied over the last 1,000 years and how that might then influence atmospheric air temperatures.
Okay, and you mentioned this gives you a 1,000-year record, but the clams themselves only live to 500 years. So how are you looking back this far?
The individual shells will only live for a maximum of 500 years, which in itself is extraordinary and would give us a fantastic record. But to be able to extend the record backwards through time, we're able to basically employ statistical techniques borrowed from tree ring analyses. And what we can do is, because any shell that's living in the environment at the same time will essentially have a barcode of ring widths. And that's to say that basically, if it's a particularly warm year, all the shells that are growing will lay down a particularly wide growth increment. Conversely, if it's a particularly cold year, they'll all lay down a narrow growth increment. And so if we have, say, a live collected shell and some fossil shells, if they lived at the same time, they'll have this same pattern. So we can then basically statistically combine these records together to extend the record beyond the lifespan of just one individual.
Okay, so then you can, by overlapping the shells, you can kind of get a year-by-year record, I suppose. So what has this told you about what the climate's been doing for the last 1,000 years?
Well, the first thing we wanted to test was the variability that we're seeing in the modern climate. How does that compare to what we've seen over the last 1,000 years? And using this record, we've been able to say that the changes we're now seeing in this record is unprecedented over the last 100 years relative to the last 1,000 years. One of the more kind of surprising things that we found in this piece of research was that a change in the natural timing of the coupling between the ocean and the atmosphere. So over the pre-industrial period, we found that the oceans played a very active role in driving the atmospheric air temperatures over the northern hemisphere and Greenland. But over the modern period, over the industrial era, we found that the atmosphere is responding much more rapidly to greenhouse gases and causing the rising air temperatures. However, the oceans were not responding anywhere near as quickly, and so there's been a shift in the temporal coupling between these two systems, between the natural system in the pre-industrial era and the industrial period that we're now living in.
David Reynolds, and that work was published in the journal Nature.